with where we have ended last time. And I will say we were talking about acceleration. And when we talk about acceleration, we need to include some of the equations that we frequently use in these calculations. Then the main topic for today is going to be the motion with constant acceleration. And always you are going to find a question where we are going to say that you can consider the acceleration is constant. Now, one thing that I want you to know that if we were, having a situation where the acceleration is not constant, either you're gonna dissect your question into like intervals where you can assume that the first one is constant acceleration 1, constant acceleration 2, constant acceleration 3, whatever. And I will say, like sometimes these situations, they're going to be very complicated. Okay, but I will say this is my advice. Now, where the instantaneous and average accelerations are equal, we are going to find that we have constant acceleration, which means it will not change. Now, there are a set of equations that we can use in this type of motion. The first one is this one here. A average is V minus V0 divided by T minus T0. If I will choose my initial time to be 0, then this is the equation that I can use here. And what I can do, I can rearrange. Then I will say V should equals V0 plus AT. Now, here I want to say something more than this, and this is the reason why I'm going to add another page where I will define for you what is really what V stands for. V here stands for my final velocity. And since it is a velocity, then it is a vector, which means it can be plus or minus. I want to bring to your attention that any velocity to the right is going to be positive, to the left negative, up positive, down negative. Because when we will move to free fall questions, you will find that you should differentiate between throwing up and throwing down. Okay? Now, of course, it is measured in meters per second. Also, I will say V0, it is your initial velocity. And again, it's a vector again, which means it can be a plus or a minus. And also it is measured in meters per second. A, it is the assumed constant acceleration. Then this is the acceleration. Again, it is a vector. Then it has a plus and a minus. It is measured in meters per second square. The reason that the acceleration, it is measured in meters per second square, that it is defined as change in velocity per unit time, and the unit for velocity, change in velocity, it is meters per second, and I have seconds for the time, and this is the reason why it will be meters per second square. Finally, the only scalar quantity here, it is time interval, and that is in seconds. Okay, then this is the first equation. And usually what I do is in my calculations, I prepare usually I like to do that, let's say a table here, because in each of these, you will find in each of these equations, I have 4 quantities. And then here I will say three of them, they will be known, and one of them is going to be an unknown. Then here I will say, for example, here, if I will use V meters per second, V0 meters per second, A meters per second square, and T in seconds, then you might be given, let's say, these three, and the question is asking about this, or any any set of variables. Now we're gonna try that equation. Then I will say there is a car that starts from rest and moves with a constant acceleration, like the question is saying it frankly. Then as I said, I like to have that table here for my quantities. I feel I am more comfortable when I have these written in that table. And I will say, when it's gonna say starts from rest, this means that my initial is 0. There are some of the key words. Okay, and moves with a constant acceleration, and that is 4. Okay, how fast is the car traveling after 6 seconds? Then this is the time, and that is 6, and then they are asking for meters per second. Now what I can do is, here I know that I'm going to use this equation, but if you will be like outside this setting, and then you need to decide based on the quantities that were given to you, which equation to use, because we are going to go through like listing more and more of these, I would say, equations, and then you need to choose this one among the 4 equations that we have, which I will talk about today. Okay, then here, this is what I'm missing. Then I will say here, I know that this is the equation here because I said this is an application of that. This is 0 plus A, it is 4 times T, which is 6. And it's very clear that one of the seconds is going to cancel, and we are going to have, okay, V equals 24 meters per second. And just again, emphasizing the importance of significant figures. My numbers, they were here. Okay, like if you look, this one 2 significant figures, this one is 2 significant figures, then I'm gonna keep in my answer 2 significant figures. Okay, then this is the first equation. Now I can also, okay, manipulate my equation, and I can derive just here another equation that I will be using. Now I will say here, using this equation, I will be able to say, okay, let me write this here, x equals x0 plus V0t plus 1/2 AT squared. This is my second equation. Okay, now there are many occasions where you're gonna have your x0 equals 0, and here where your equation is gonna, or you can use your coordinates so that this is the case, and then this is the equation that we have the second one. Okay, now I want to say that all these equations are really they are equivalent. Okay, one of them is not more important than the other, but the thing is, sometimes I need to choose between them, and most of the time I will have only one of them which is gonna work, and this is the reason that I will use it, this one rather than using the other one, because this is the one that is gonna work. Also here, I want to say something about so that you will not be confused. In the previous lecture, I did say that we cannot say V average is the, adding the velocities and dividing by their number. There is an exception that only if I have constant acceleration motion. Then if I have constant acceleration motion, I can use this equation. But if I don't have that situation, this is not a general equation. Okay, now I want to try to use the second one, and I will say here that this is like the same, maybe exact, but like it is modified. Then I will also have my four quantities listed here. A car moves starts from rest. And moves with a constant acceleration. And after 6 seconds, they are asking me about how far the car has traveled. Then I am looking for X and X in meters. Now you can add another cell here and say here, like I can choose my coordinates to have my initial, my origin starts from X, where at t equals 0, X was 0. Then X0 is going to be 0. Now here, we know that we are going to use this equation here, which is X equal X0 plus V0t plus 1/2 AT squared. Here, two of the terms are 0. This one is because my initial displacement was chosen to be 0, and the second one, it is because the initial velocity was 0. Then I will say X equals 1/2 times 4 times 6 squared, and that is a calculation that we need to do. And remember, we need to stick with the significant figures, and that is I will say is gonna be 72 meters. And again, keeping 2 sig fig because of the initial problem has 2 only. And when we do the multiplication, we're gonna keep the same. All right, now I can now build on having another equation, and that equation is gonna be rearrange it like this is easily the derivation, but we can rearrange it as v squared equals v0 squared plus 2a times delta x. Now again here I will say like these are the same variables that I did use before. This is the final velocity, and it can be plus or minus. This is the initial velocity, and also it is meters per second. It is the acceleration. Again, it can be plus or minus. Now delta x, it is displacement, which is of course change in position, x minus x0. It is measured in meters, and again it can be plus or minus. Then now I have that equation again, which is again the third equation that I can use, and that one is going to be again equivalent to all the 3 before. I want to try it, and then this is where I will okay, start solving this one. Now remember, I will say I'm doing this like just without maybe talking about the steps of the problem solving, but usually it is good, it is recommended. Let's say that I want to draw a diagram, okay, and when I want to draw a diagram, then I will read the problem and see what is really the, you know, the things that I'm talking about. Landing with a speed of 81.9 meters per second, then here I will say there is an airplane here, and that airplane is just landing. Okay, then when it is landing here, I will say, okay, let me have also my quantities here. Then my V0 here, it was 81.9 meters per second. I can say negative because it said south, okay, then it is south. And traveling due south, a jet comes to rest in, then it will here, finally. Okay, this is my V initial was 81.9. And then here the final was 0. And a jet comes to rest in, then this is the displacement. Then this is x minus x0, which is 949. Then you can make it like either you can, like you use it delta x. You don't have to worry about the initial. Find the magnitude and direction of its acceleration. Then the acceleration in meters per second, I want to calculate that. Now also, since the object is moving south, I can make that also negative. Now the acceleration is my focus here, and I know that I will use v squared equals v0 squared plus 2a times delta x. Now this one is 0 squared, this one is negative 81.9 plus 2 times negative, a first, and then I will have that, I want to write it here, 949 meters, okay? From that, you're going to get, let me do this in more steps so that you will not be confused. 0 equals, I need to square that number. And here minus 2 times the 949, which is 1898. Then A is going to be the number that is 6707.61 divided by 1898, and that is 3.53 meters per second square. Now you can see that the acceleration here, it is positive. Okay, then, okay, the direction of the acceleration is up, and the velocity was down. Okay, this means that the acceleration is in the opposite direction of the motion, and this is why I will say velocity decreases, or like speed decreases. Here I want to announce the what is called the exit ticket 2. Okay, the exit ticket 2 is going to be free response questions. You will find them by the end of this lecture. There is a handout called linear motion handout. That one you are going to solve number 4 and number 8. Number 4 and number 8. You're going to have them as free response. You're going to show all the details of your work. There is a link on Canvas. You will find it, exit ticket 2, and it said chapter 2B, which is this lecture. You will solve number 4 and number 8 from the handout by the end of this written notes, and you are going to submit them. You scan your work and you submit via Gradescope. Now here also I will say some of the most important things that we know about applications of the equations of motion is when you hit the brake and this was your initial velocity, then you will start slowing down, right? But the thing that you will have a stopping distance, okay? And that stopping distance is gonna change a lot with your velocity. Then it has to do with your speed initially. And in this here diagram, I have maybe the speed was about, let's say, 12, and you will reach 8. The speed is going to be 8 at half of the stopping distance. And then, just to think of this, you need to always to consider that your stopping distance depends on your initial speed, and then you should be able to, manage your speed so that you will not go to this kind of accidents or stuff. I will add also another equation that I usually like to add based on, I said they are 4, and the one that maybe usually it's not listed in most of the textbook, but I like to list it here. It is this one. Okay, it is derived, all of them are derived from the same source. And then here, x, it is your final position, and it can, again, plus or minus, and it's gonna be in meters. And x0, it is your initial position, and in meters again. And the velocities are the same. Remember also, I can write this as, okay, this is when I have accelerations, okay? And I want you to know that if we have motion with a equals 0, means constant velocity motion, okay, x equals distance divided by time, as easy as that. V, okay, V is distance divided by time, and then from that, distance is V times T. Okay, this is this equation only we can use it when we don't have any acceleration. All right, now let me also, there is another one here, another problem that I will go over. And that one is another type of braking, like you have a bullet or you have any kind of thing that is going to go through an object, and then the frictional force, they're going to stop it. And I will say here, I'm going to again read my question and maybe also draw something. Then there is, on October 1992, a 27-pound meteorite struck a car in Peekskill, New York, leaving a dent 22 centimeter deep in the truck. Then that is really what I need to know, that there is, I will assume this is the thing, and then I have that whatever it was, meteorite or anything that is gonna go deep inside like this. That distance here, it is x minus x0, 22 centimeters, and don't forget to change this into meters. And also I can work on my variables here. Okay, my delta x in meters, it is 0.22, and then the initial velocity was given as 130, and of course finally it will stop. Okay, you need to understand this from the physics or from life. And here I am looking for the acceleration. And here I will say, I can list the equations and try to find, like, okay, usually it's helpful for me to list the equation to find out which one I will use. Then I am listing the equations here. And I will say, if I compare, I know that I will be using this one. Then I will say, this is the first step in the solution. I will choose my correct equation here. And my velocity is 0, the final. The initial, it was 130. And I don't know what's A. Okay, and then here you will find that the acceleration is going to be negative, and this is of course making sense because it should be, because it's gonna cause the speed to decrease. Then this was the acceleration. Wow. Okay, and it is negative. Okay, now here I have 2 sig fig. Then I will say this is my correct solution, to consider only 2. Or what I can do is I can make this to be like more 4 meters per second square. Okay, so that I will have only 2 sig fig, because remember this one, the first one we said ambiguous, also, although like I can say it is 2, for me, like sometimes I consider it correct. Okay, now the last topic in this chapter is about falling objects, and this is an example of constant acceleration motion. Why is that? Because we are considering that the objects in a free fall, they will have a constant acceleration, and here we are assuming no air resistance. And it was first maybe like proven by Galileo that when rocks were dropped from the tower, they sped up as they fell, and we can actually verify this, and they will accelerate at the same rate. I will show you here two videos to maybe to talk about this idea. Okay, where is my here? Okay, where is my physics? Home. My library, my physics. Okay, I want to show you first the MIT one, which is the last one here, I believe. Okay, that one. You can see that the distances are increasing. Okay, you can see, which means that object is moving with acceleration. Now, also, I want to share with you another one, which, okay, the thing that we waited till we did reach the moon, and then we were able to prove that all the objects, they accelerate with the same rate. Just let me find it here. Where is, yes. Yes.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got the...
Beautiful picture, Dave.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Okay, this was the hammer versus feather, where we were able to prove the Galileo experiment. Okay, now here, when we talk about free fall, we are talking about that objects that they are not actually under the influence of other forces than gravity. It's only gravity. Okay, then there is no air resistance. Okay, but of course, if I have air resistance, like you see here in the, let's say I have like a ball and a sheet of paper. Okay, this will not work. Okay, on the moon there is no air resistance, and this is the reason why we were able to do that. Okay, now we are going to use the same set of equations for a free fall. Okay, and then this is where I will now start. Okay, then it's the same set of equations, but we are going to know our acceleration to be, okay, it's downward, right? And because of that, it should be negative. It is negative 9.8 because it is downward and it is constant near the surface of the earth. Then always on these free fall, only in free fall, a meters per second square is going to be known always. Okay, and here I have my numbers too. Then I'm going to keep 9.8. Okay, let's say I drop. When I drop, this means that my initial velocity is 0. From the top of a tower that is 70 meters, then I will say I am here at the top of this tower, and then I have dropped my, okay, and dropped means, as I said, from initial equals 0. And since, look here, this is, I'm gonna use delta y because I am moving vertical. And since I am moving downward, my displacement should be also what? Negative. And then how far will it have fallen in 2 seconds? Okay, then this is the time, and it is 2 seconds, and we want to know what is really y at this time. Okay, now also I need to have my coordinates here. It's very important. This is my x, this is my y, this is my 0, 0. Okay, so that my y0 is 0. Okay, now what I'm looking for is this. These are my 4 quantities. I'm trying to find an equation among these here that I will be able to use it. And I need to have the displacement. I need to have the initial velocity. I need to have I need to have time. And here I will say, okay, that is my equation that I will use. Okay, and here I will say this is y minus y0 equals v0t plus 1/2 at squared. Now this here is 0 and this one is 0 because the object was dropped. Then I will say then my equation y, it is 1/2 at squared. Now y is negative, no, I want to find my y here. Okay, then in this first part. Well, this is 1/2 negative 9.8 times 2 seconds is squared, and that is going to give me 9.8 times 2 because one of the two is going to cancel, and this is going to be negative 19.6 meters. Okay, and that is really negative because the object is hidden down, and of course I did say y. Now how long will it take to hit the ground? Then now is gonna cover all the distance or the displacement, and here I will say I'm gonna consider now, okay, this, okay, this, and now the time is missing because I need to find the total time. And I will say again, I can use actually the same equation. Then delta y should equals v0t plus 1/2 at squared This is 0 again. This one is negative 70. And this is negative 9.8. And remember, if you forgot one of the minuses, the solution will not be, you will not be able to find the square root. Okay, even if you put it without negatives, I will consider it wrong. The reason is you are telling me that the object is moving upward because your numbers are positive and it is accelerating upward, which means something from in the heavens it's attracting, which is not correct. Okay, then here I have to calculate first 70 times 2 and then divided by 9.8. This is gonna be t squared equals 14. Like you can put all the digits here, and of course using your calculator you will be able to find what is really the, I will say t, okay, sorry, and that is gonna be 3.8 seconds. Then it will take 3.8 seconds to reach the ground. Now this question here is gonna be about throwing. Throwing is different from, okay, I would say dropping. The dropping means it is 0. Now let's say that I throw my physics book downward. Then here it's the same, but I am giving my, okay, an initial velocity, and that initial velocity 5 meters per second. Then now the story is gonna be different, and I will say here again, okay, this is V initial, and it is negative 5. Okay, let me, so that I will not confuse you. I did, like in the diagram, I don't need to put negative because I did show that the vector is downward. But so that you will not be confused. Negative 5, and again, delta y, it is negative 70. And I have A known always as negative 9.8. And I need to find how far it will travel in 3 seconds. All right. Now, what I have here is I want to find again. I'm gonna add here y. Okay, and then here y equals y0 plus v0t plus 1/2 at squared. My initial, I will use my coordinate here. Then this is my 0, 0, then my y0 is 0. And negative 5 times 3 seconds, okay, plus 1/2 negative 9.8 times 3 seconds squared. And here I have to find 5 times 3 first, then is gonna be y negative 15 meters, and here negative. Okay, then remember here, if you will forget your negatives, the answer will not be correct. And then this is gonna be the total displacement, negative 9.1 meters, but it is downwards, okay, because it is negative. Now, how fast? The second question is how fast. Okay, how fast means V equals V0 plus AT. And then here I will say it is -5 initially and -9.8 times 3 seconds. There is no square here. Then what you need to do is you are going to multiply 9.8 times 3. It should be again negative, and you're gonna add the -5 to it. Then the final velocity, it is -33.4. I need to consider only -34 for the sake of significant figures. One more problem is I'm gonna do one more, okay, because these are really like I will leave these for you to attempt, and if you have any questions, let me know. Okay, I'm gonna solve one more, which is this one here. Okay, and I will say here I have again, this is my, okay, and I will say in this problem here I will solve, okay, this is like V0, it's upward, all right, then V0 is 15, and it is positive because it is upward. I want to find when it is at the maximum height, what is going to be like that maximum height, how high and how long is gonna take it. Now, one thing that I want you to know, that when we have the maximum, V final is gonna be 0. And again, I can have my coordinate, this is X, this is Y, and this is gonna be 0, 0. Then my final velocity here, because it did reach the maximum, is gonna be 0. And I know that the acceleration, it is -9.8. And the first question is asking how high, then I am looking for my delta Y. Okay. If you look carefully at like the equations, this is the one that I'm gonna use. Then it is V squared I change my X into Y because I am talking about vertical motion. And then here this is 0 squared, this is 15 meters per second. All right, and to -9 point, I should use here, sorry, 3, because although in your textbook they are using -9.81, I don't like that. We're gonna use -9.8. And finally, I am looking for my delta Y. Then my delta Y is going to be 15 meters per second squared divided by 2, 9.8 meters per second squared. Now, the 2 here, it is an exact number that will not affect my significant figures rule. Okay, then this is a built-in number in the equation and it will not affect it. Okay, then here this is a plus 11 point, like there are so many digits, but 11.5 meters for the sake of significant figures. How long will it take to fall back to your hand? how long will it take to fall back to your hand. Again, I can draw here, and this is my, okay, it did reach here, and then it will go back to my hand. And remember, this is my 0, 0. Then what I can do here is my y is going to be 0. Then, okay, this is one of the solutions. There are so many solutions, but this is the easiest. I will say here, delta y is going to be 0 because it came back to the, and remember, this is displacement. It came back to where it was really launching from, A. And I'm looking for how long, then I'm looking for the time. Also, I have the initial velocity was given as 15. Now, what I can do is, again, I can have this equation, V0t plus 1/2 AT squared. Now, this is 0. This is 15 meters per second. T is not known, plus 1/2 negative 9.8 times t squared. And from that, like, I can move this one to the other side and have that negative 9.8 divided by 2, which is 4.9. You can drop one of the t's here, then your t is going to be the 15 divided by 4.9. Sometimes you have to use the quadratic formula for some of these like solutions. Then this is the total time. There are other techniques that you can use. You can find the time to reach the maximum and then multiply by 2, because this is really the, you know, the situation where we don't have a resistance. All right, and just for the remaining part, these two, like if you, 3 actually, if you want to attempt, go ahead. Here is the summary of the chapter, talking about the most important, I would say, definitions and things. And this is the linear motion handout that I was talking to you about, which is